What's up guys, today we're going to be solving the Leetcode hard problem trapping rainwater. So given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after remaining. So if you take a look at this example below with the elevation map provided in black as the input, we can fill up water in all the areas highlighted in blue for a total of 6 units of water. So now let's solve the problem. So instead of solving the problem of figuring out how much total rainwater our entire system can trap, let's analyze how we can solve the problem of how much water we can trap at an arbitrary index I. Because if we're able to figure out how much water we can trap at a given index I, well then all we need to do to figure out how much water our total system can trap is simply by summing up the amounts of water we can trap at each index I. So we want to solve this overarching subproblem, how much water we can trap at index I. Now the first thing that we need to answer though is, can we even trap water at index I, right? Can we trap water at index I? Because there are going to be indexes within our system in which we cannot trap water. We can't trap water at I equals to 0. We can't trap water at I equals to 1. We can't trap water at our last index. So can we trap water at index I? That's the first question that we need to answer. Well, we can trap water at index I if there exists an index to the left, j, and there exists an index to the right, k, such that the height of index j and the height of index k is greater than the height of index I. And why is this the case? Well, in order to trap water at any index, we need to have a left bound and a right bound. In other words, when I say left and right bound, I mean these indexes to the left and the right that have a greater elevation than our current index. That way we can trap water because it's going to be bounded both on the left side and bounded on the right side, right? So just to take a few examples, we can trap water at index I equals to 0, 1, 2, 3, 4, 5, 6. We can trap water at I equals to 6. Why? Well, because index I equals to 6, its elevation is 1. There exists an index to the left of I equals to 6, specifically at index I equals to 3 with height 2, which is greater than 1. Conversely, or similarly, there exists an index to the right of I equals to 6 at I equals to 7 that has height 3 greater than height I equals to 1. So because I equals to 6 is bounded both to the left and the right, we can fill up water at I equals to 6, right? That's just one example. There's many other examples too. At I equals to 2, we can fill up water at I equals to 2 because I equals to 2's height is 0, less than the previous index's height of 1, less than the subsequent index's height of 2. So we don't just want to figure out whether or not we can trap water at index I. We want to figure out the maximum amount. And by how much water, I mean the maximum amount of water we can trap at index I. Which means that we need to choose the maximum possible value for hj and hk, right? We want to find j and k such that hj and hk are as large as possible, right? Now, if we find hj and hk that are as large as possible, that's going to allow us to trap the most amount of water at index I. The question now becomes, which bound do we choose? Do we choose hj or hk as the level in which we can fill up water to at a particular index I? Well, we're going to choose the minimum of hj and hk, right? Because if we choose one bound that is greater than the other bound, then we're going to have an overflow situation. So for example, at index I equals to, or any index in between I equals to 3 and I equals to 7, the maximum left bound is going to be at height 2. The maximum right bound is going to be at height 3, right? Now, if we choose 2, we can fill up water perfectly fine. If we choose height 3, which is greater than the left bound at height 2, well, then we're going to have a situation where the water is going to overflow. It's not going to be bounded, right? So the level of water in which we can fill up to at an arbitrary index I is going to be the minimum of the maximum possible value for h of j and h of k, okay? So That's good, right? So choose h of j so choose the minimum of h of j and h of k as the level of water that we can fill up index I to, right? That's all good. Now, that we're not done solving this problem though, right? Because the amount of water we can trap at index I is simply going to be the level of water that we can fill up index I to, subtracted by the height at index I, right? Because if we take any index, for example, at index I equals to 0, 1, 2, 3, 4, right? How much water can we fill up at I equals to 4? Well, we can fill up water all the way up to 2, right? Which is going to be derived from a minimum of h of j and h of k. But we also have to subtract the height at index I, right? Because we can't fill up water in the units that are already occupied by the elevation at index I. So this expression is going to answer the question, how much water we can trap at index I, right? So this expression is key because once we're able to compute this expression at each index I, well then to solve this problem, we just need to sum up this value for each index I, right? So it's a simple summation problem after that. So this is the general algorithm that we have, right? We use this expression to figure out how much water we can trap at index I. Then we just need to iterate through each index and then add this quantity to our result. And we're going to add this quantity if it's positive, because if it's 0, then it doesn't impact the result. And if it's negative, well, we're not going to add that, of course, the result, because it's impossible to fill up water to a negative degree, right? That doesn't make any sense. So that's the general algorithm, okay? All right, now that we have the algorithm done, let's talk about the data structure that we're going to be using, right? So to store the left bounds, the max left bounds, we're going to be using an array to store that, right? And then max left bounds at index I is going to be the max h of j, right, with j less than I, right? Similarly, max right bounds I is going to be max h of k with k greater than I, right? Now, to solve this problem in linear O(n) time, the way in which we populate these two data structures is very important. Usually for these coding interview problems, you want to solve it in linear time preferably. Usually that's the optimal time complexity. There are situations where you can solve a problem in constant O(1) time, not in this case though. But you want to usually get it down to linear time. Now, the way we populate these data structures is important because it's going to impact the time complexity. Now, for max left bounds, we want to populate it from left to right, and for max right bounds, we want to populate it from right to left. And the reason for that is because the range of values, right, from 0 to I exclusive is simply the range of values from 0 to I minus 1 exclusive plus I minus 1 in and of itself, right? Which means that obviously max left bounds I is going to be equivalent to max left bounds I minus 1 is simply going to be the maximum of max left bounds I minus 1 and height at I minus 1, okay? And it's the same logic, right, for max right bounds. It's just reversed. So once we've populated these data structures, right, all we need to do is just iterate through each index, right, find this quantity by looking at these two data structures and then subtracting the height at I, and then we add it to our final result, again, if it's positive. So now that we have our algorithm done, let's get down to the coding. So the first thing that we need to do is handle the base case, right? Because we can't fill up water at the first and the last indexes, right? That should be obvious because the first index is not bounded to the left, the right index is not bounded to the right. So in the case that we only have the first and or last index, right, which means that height.length is going to be less than or equal to 2, right, we're going to return 0, right? Next, let's define our data structure. So we'll set n equals to the length of the height array. We'll have left bounds equals to a new integer n. And let's call this max left bounds. We have max right bounds equals to new int n, and then we have the variable storing our total result of all the water that we can trap. That's going to start out at 0, right? So again, as I stated before, we want to iterate from right to left to fill up max left bounds, right? So if for int I equals to 1, I less than n minus 1, I plus plus. So again, we're going from index I equals to 1 less than n minus 1 because we don't care about the first and the last indexes. It's impossible to fill up water at the first and last indexes. Max left bounds I is going to equal to math.max max left bounds I minus 1 height I minus 1, and then we just need to do the reverse for max right bounds. So for int j equals to n minus 2, j greater or equal to 1, j minus minus, we're going to have right bounds max right bounds j equals to math dot max right bounds j plus 1 height j plus 1. So we filled up these two data structures. That's the first step. The second step is that we need to iterate through each possible index and add up the amount of water we can fill up at each possible index. So for int k equals to I, k less than n minus 1, k plus plus, we're going to say total plus equals to... First, let's figure out, okay, so because we need to check whether the amount of water that we can fill up at each individual index is positive to begin with, right? So int water, trapped water at trapped water equals to math.min. We're going to need to take the minimum, as I said before, right, of max left bounds k, max right bounds k, minus height of at k, right? And then if trapped water is positive, we're going to add that to our total result. And then finally, all we need to do is return total, and then yep, this looks good. This should run in on time and space. It's going to run in on time because we're doing linear walkthroughs. It's going to run in on space as well because we're using arrays the length of the input height array. So let's run this code. Looks like we have an extra space. All right, let's submit it. Yep, looks like we solved this problem. Okay, so yeah, I did the solution in Java, but in the future, I actually plan on doing C++ solutions as well because I'm trying to sharpen up my C++ skills. But let me know what you guys think. That's solving trapping rainwater for Leetcode. I think this was a great problem. It's a pretty common problem that's asked, especially at FAANG companies like Amazon, Facebook. So let me know what you guys think. Don't forget to like, comment, subscribe, and I'll catch you guys in the next one.